do a line integral example where it's not as trivial as over a line segment. So I'm going to do some integral where my curve is now going to be the intersection of two cylinders. These are cylinders because it's a circle in the xz plane. So the y-axis coming out, or in 3D, looks like a cylinder. Set up the parameterization. Sum of squares grouping, right? We're going to be doing polar, but it's not xy polar. First thing, we'll see what the curve looks like. Two equations, it's a curve. So I need to start solving for variables. Subtracting the equations. I can solve for y in terms of x, it's plus or minus. So we're looking at two curves. Y equals x and y equals minus x. Call them C1 and C2. So let's set up C1. I'll pick one of the equations to make my r squared. So I'll get my change of coordinates. X and z are now the polar, y is still y. And get my two equations, r is 1, y is x, and substitute to get my parametric form. R is 1, y gets replaced with what x is, and r is 1. One parameter object, and there's my curve. There's no restriction on theta. Now it's the easy part. Now that we've got our parameterization, we just plug it in. Set up my vector form. Take the derivative. ds is length r prime, d theta. Sine squared is 2 sine squareds plus cosine squared. One of the sine squareds and the cosine squared will turn into a 1. And there's my ds. Plug it into my integral. So instead of summing over points on the curve, I'm summing over the parameter values on the curve. Replace z by its parameterization. Replace ds by its parameterization. There's my C1 curve. The C2 curve is exactly the same, except y is replaced by minus x. There's no y in the integral. In the differential, the sign doesn't matter because it's squared, so it's just two of the same integral.